Okay, good afternoon, everybody. Apologies for this being so late today. I've been doing maths interviews this morning and everything's just got a bit too much. But yeah, I've got time to do this now, so we'll get this done and then you guys can enjoy a bank holiday weekend and hopefully some good news on Sunday about lifting some of the lockdown. So what we're going to look at today is something which we looked at a little bit a little bit earlier in the year. I think I wish in hindsight I'd left it till now and done it a bit better. We are going to do it now. And I'm going to give you a flow chart for this to help because this wasn't done so well by many of you in a test which we did. So what we're going to be looking at is the intersection of three planes. One of the sheets which I'll attach to the class charts I put on the VLE will show you the 5 different ones. You've seen them before, but if some of these words like sheaf don't make any sense, if you look at the sheet I'm going to stick on the VLE and class charts, you'll be able to match those up so you can see what they look like. So if you have an intersection of planes, there's 5 different situations. Either all of them are parallel, in which case that they definitely don't intersect. 2 are parallel. If 2 are parallel, then the other one must go through them. The planes intersect at a single point, so they're all perpendicular to each other. Planes form a sheaf, so that's when they all meet on a line. So they all meet on a line. They all sort of go off in their own little way. That looks a bit like a bit like a propeller or something like that, possibly, or something from a generator. And the last bit, planes form a triangular prism. So that's exactly how it sounds. 2 planes intersect each other, but all 3 don't intersect each other ever. So there are 5 different ones which we need to look at, and hopefully you can see that, or think about this, that this one, if they meet at a singular point, or this one, they form a sheaf. These are the only 2 where you could actually get some sort of solution for where these planes meet, because they're the only 2 situations where the planes actually all meet together. The triangular prism, the parallel ones, at no point do all 3 meet at either a point or on a line. So what I want to do is just go through a quick flow diagram of how you can decide which of these 5 it's going to be, and I'm also just going to tell you the tools that you will need to follow the flow diagram. So the tools that you need are to be able to work out a determinant, check. To be able to work out what the normal vector of a plane is. So if you've forgotten what that is, if you've got ax plus by plus cz equals d, then a normal vector of that plane is a, b, c. If 2 planes have the same normal vector, then they are parallel to each other. They might even be the same plane. Consistent solutions. So that's what we did the other day, actually. We did that when we were doing, crikey, what were we doing? Let me have a quick look back. So I'm just reminding myself now. When we were looking at skew lines the other day, we solved for 2 of the equations that we got and then tried to see if they were consistent with the third one. In other words, if they were consistent, then a point existed that solved the equations. So in terms of this, we're looking for consistent solutions. In other words, is there something that solves the equations, be it a point or a line of points? And I'll go through a particular one of doing that because that's sometimes the more awkward bit of all this. Okay, so what's the process or the sets of checks you need to go through? Well, here they are. So the first thing you need to do is always check whether the determinant, this is the start point, probably should have written something there. So the determinant of M, so your matrix, so what do I mean by M? Well, if you've got 3 planes, remember you can put those 3 planes into a matrix. And I'll just do a little example of that up here, actually. So if I had x plus 2y plus 3z as one plane. Let's say that just equals D1. I'm not going to be very inventive. Okay, so here's my three planes, x plus 2y plus 3z equals d1, etc., etc. This is just some value. I can put some value. This could be 11, 12, 13, whatever. It doesn't really matter. The important bit is what's going on this side. So I could rewrite this left-hand side as 1, 2, 3, 4, 5, 6, 7, 8, 9, x, y, z. And I can just rewrite the right-hand side with some brackets around it. If you multiply this left-hand side out, you'd pick this vector up, bang it down the matrix, and you'd end up with 1x plus 2y plus 3z, 4x plus 5y, etc. And they would all be equal to these values over here. So the top line would be the top plane, the second line, the second plane, etc. Okay, so when I say the determinant of them, what I mean is the determinant of this matrix here. So if the determinant of that matrix is, so you check if it's 0. If it's not 0, that means m is non-singular and there is a unique solution. So the planes meet at a single point, they're all at right angles to each other. That's the simple variety. If not, sorry, if it is equal to 0 even, then m is singular, and then you need to check whether the equations are consistent or not. So, excuse me. If they are consistent, then you have a sheaf, and if they're not consistent, then you need to check for whether they're parallel or not. If some of them are parallel, then you've got either 2 parallel planes or possibly 3. If there's no parallel planes at all, then you end up with a triangular prism. And this is the sort of stage you need to go through. One thing on this though, if you can look at a set of planes straight away and see if they're parallel, and I suggest this to you, always have a quick check for any parallel plane straight away. Because if two planes are parallel to each other, there definitely isn't a unique solution to all 3. So yes, in general, if you follow this flow diagram, you will always get to where you want to go. But before you start, just have a quick look, see if you can see whether 2 planes are parallel or not, because that will sort things out straight away. Like I said, how do you check whether 2 things are parallel? They'll have the same normal vector, or their normal vectors will be a multiple of each other. Okay, so if this plane was ax plus by plus cz equals d, and another one was 2ax plus 2by plus 2cz equals d, then one would have this normal vector, the other vector would have 2a, 2b, 2c. They're multiples of each other. Essentially, they're the same normal vector. They're in the same direction. Okay, so what I'm going to do next is just run through one example, and then I'm going to leave you some work to have a go at and make sure that you guys get better at this skill. Okay, so let's have a go at this question here. Determine the arrangement of the following planes. Okay, so like I said, have a quick check for normal vectors. Well, I'm just going to write the normal vectors next to them. 1, minus 2, 1. 1 minus 3, 3. And 2 minus 7, 8. So I can see from there that none of these are multiples of each other, so I know they're not parallel. So I can kind of actually get rid of that choice box in my flow diagram now. So now I'm going to find out what the determinant of the matrix M is, and hopefully it's going to be a unique solution. Otherwise I'm going to have to do some more work. So can you guys have a go at that first? Can you write down what the matrix would be, and then can you have a go at working out the determinant? I don't mind if you do it by hand or on your calculator. I would suggest you do it the way you feel least comfortable doing today, because you'll get better at that method obviously in the exam. If it doesn't stipulate, then just do it the way you feel most comfortable with. Okay, so just pause the video and have a go at that and come back to me, please. Okay, so hopefully you got this matrix. I'm sure we've done this before, but if you put straight lines on the side of the matrix, then that's saying I'm working out the determinant of this. So I've got 1 times this minor, minus minus 2 times these minors, and then 1 times the minor here. That gives me minus 24 plus 21 plus 2 times 8 minus 6 plus minus 7 plus 6. Doesn't feel quite right, but let's go with it anyway. So 21, so that's negative 3. So that's why. Actually, that's the brackets around it. 2 times 8 minus 6. 8 minus 6 is 2, plus 2 is 4. And minus 7 plus 6 is minus 1. So that equals 0. So because it's 0, there is no unique solution. When doing these, it's a really good idea to specify to the examiner what you are doing and why you are doing it, because it's so much easier to give you marks. If you just do a series of calculations, it's not always obvious why you've done that, especially if you make a mistake. So therefore, there's no unique solution. Interestingly, if there was a unique solution at this point, then it might be the case that you need to work out what the unique point is. In this case, you would need to find out what the inverse of this matrix is. And the reason for doing that, as I'm sure you'll recollect, is if you know what the inverse of this is, if you times both sides by the inverse, you'll be left with what the point is, and the matrix times this will give you what that point is. So that's why you might want to find out the inverse in this case. Some of the examples I've left you, I'm going to ask you to try and do that by hand. Others I'll ask you to do it with a calculator. Okay, so there's no solution. So next we need to check, are the equations consistent? So the way to do that is first of all by writing them out again and labelling them 1, 2 and 3. So again, people can see what you're doing. Now, if these equations are consistent, then obviously there is a line. We know there's no unique solution, but there could be a line that all of these planes intersect on. So basically the idea of this is saying, okay, well if I concentrate on one of these equations and manipulate it with, so let's manipulate 3 with 2 for instance, to get rid of one of these variables. So if I get rid of z for instance, then I'd be left with something which has got only 2 variables in other words a line. So if I worked on 2 of them first to reduce them down into a line, and then let's say I do the same thing with 3 and 1 and reduce that down into a line, then these things are consistent if that line is the same. The reason for that is if the line that these two intersect at and the line that these two intersect at is the same line, then they all intersect in the same line, and if it's not, then they don't, and so there can't be any solutions at all, hence they're not consistent. If that doesn't make too much sense, have a look at the picture of a sheaf and then try and listen back to what I've just said. Okay, so this bit here, it doesn't necessarily matter which way you go, but there are definitely some better ways than others. So I'm looking at this at the moment. I'm thinking, well, I'm going to concentrate on 3 and I'm going to take away some lots of 2 and some lots of 1. The reason why I'm doing that is just because it's the easiest thing at the moment looking at this is just to kill the x's in 3. That's the only reason. So I'm going to try and kill these x's. The way I'm going to do that is I'm going to do 3 take away 2 times 1. So if I do 3 take away 2 times 1, then I've got 2x minus 7y plus 8z equals 4, and 2 times 1 is 2x minus 4y plus 2z equals 8. I'm going to take one away from the other. I would strongly suggest that you do write this out because it is far too easy to make a mistake and it takes literally seconds to write it out again. So the x's will kill each other. Minus 7 minus 4y is minus 3y. And 8z minus 2z is 6z. And 4 minus 8 is minus 4. So I could rearrange that. Probably the easiest thing is also to divide by 3, but yeah, let's just divide by 3 for now. So we end up with 2z minus y is equal to minus 4 over 3. Okay, so that is the line that these two intersect on. So now I've done that with 3 and 2, if I do it with 3 and 1 as well, I'd better get the same line if I'm getting rid of the same variable. So let's just pop up here. Starting to run out of room in this book. Okay, so I think the same. Let's do 3 take away 2 times 2. So that gives me 2x minus 7y plus 8z equals 4. And if I take away 2 lots of the second one, I've got 2x minus 6y plus 6z equals 6. And if I take one away from the other, I'm left with no x's, negative a y, 2z, and negative 2. Okay, so if I think about what I've got in my other one, I've got 2z minus y equals minus 4/3. This one is 2z minus y is equal to minus 2. 2z minus y equals minus 2. 2z minus y equals minus 4 over 3. So the left-hand sides are the same, the right-hand sides are different. Minus 2 is not the same as minus 4 over 3. Therefore, equations are inconsistent. Okay, there would have to be exactly the same line for consistency to occur. Inconsistent. I think it's an E and not an A. So that's how we can try for inconsistency. We already saw earlier that the planes aren't parallel, and so because they're not parallel, we have a triangular prism. So I'd finish by saying not parallel, because I didn't actually mention that earlier. Notice earlier I wrote them out, but I didn't particularly write anything down. The reason why I didn't write a sentence down there is because I may have found that there was a unique solution and I didn't need to write it. In fact, actually writing therefore now would be a bad idea because it's sort of based on what that is. So probably the best thing to write here is not parallel. Just write the normal vectors out again quickly. And 2 minus 7, 8. And so because that's true, then we can say that it's a triangular prism. So as long as you get that information across, it possibly is better to write that not parallel thing at the start. And as long as you have conclusions from when you do something, then you should be able to find out the arrangement of any 3 planes given to you. You'll need to remember that that flow diagram that won't be given to you in any way, shape or form. So try and think about how you can remember those checks and in which order you're going to check them in. Okay, have a lovely long weekend. If you still have some work to hand in, please hand work in. Mr. Clark is racing furiously to get work done and get it back to you. And I will just make sure that the questions for this lesson go up today. And I'll speak to you again next Monday. Bye-bye. Have a good weekend. Bye-bye.